Hi, today I'm going to be talking about primordial non-gaussianity from large-scale structure. In other words, how we can study galaxies, galaxy clusters, and dark matter halos to learn about the very early universe before the Big Bang during a period known as inflation. I'll also introduce an upcoming NASA mission called SPHEREx that is going to try and measure the Gaussianity from large-scale structure in our universe to learn more about the period of inflation. So, quick review. What is inflation? Inflation was proposed by Dr. Alan Guth in 1979 when he was studying why we don't observe magnetic monopoles in our universe. Pretty much the standard model predicts that if the universe did begin in a very hot, dense state, which is what the Big Bang predicts, we should be able to observe a very large number of heavy, stable magnetic monopoles. But to this day, physicists still haven't observed any magnetic monopoles in our observable universe. So to try and solve this problem, Dr. Guth proposed the model of inflation, which pretty much states that before the Big Bang, the universe experienced a period of rapid accelerating expansion that lasted from about 10 to the negative 36 seconds to 10 to the negative 33 seconds. This model of inflation happened to solve some other big cosmological problems that were present at the time, such as the horizon problem, why the universe is homogeneous and isotropic, and the flatness problem, why the universe appears so flat. Although Dr. Guth's model of inflation forms the basis of inflationary models today, one of the most popular theories of inflation is called slow roll inflation. Slow roll inflation pretty much states that the inflating universe is powered by a particleless scalar field called the inflaton field. For the sake of this talk, I'll also define the potential of this inflaton field to be V of phi. At the beginning of inflation, the inflaton field is in a state where the potential energy is not at its local minimum. Here we have the potential energy on the y-axis and the strength of the inflaton field on the x-axis. So at the beginning of inflation, the inflaton field is at the blue point on this plot. Since the inflaton field wants to reach its minimum potential energy, the strength of the inflaton field will change until it reaches this minimum. While the potential is nearly constant and slow rolling down this potential hill, which is in that gray box, the universe is experiencing inflation. Inflation ends when the strength of this inflaton field is such that the potential is minimized. But how does this affect our universe today? Quantum mechanics predicts that the inflation field will experience quantum fluctuations during inflation. This causes different parts of the universe to undergo slightly different evolutions. And after inflation, this is what induces the density fluctuations that are known as initial conditions during the Big Bang. So the inflaton field will actually decay into the standard model particles we know in the Big Bang model. So since this inflaton field experiences these quantum fluctuations, when it decays to these standard model particles, these fluctuations will form physical density fluctuations in the universe at the beginning of the Big Bang. However, how these fluctuations form are still not completely understood. There are several models to try and explain the physics of inflation. There are single field models that predict that the inflating universe is powered by just this single inflaton field. But there's also multi-field models that predict that this inflaton field is actually coupled to some other quantum fields that existed during this time of inflation. The interactions between these fields can therefore affect fluctuations that appear during inflation and even affect how we see matter at later times. Specifically, single-field models predict Gaussian perturbations, while multi-field models predict non-Gaussian density fluctuations. The Gaussianity of these fluctuations is characterized by this parameter f sub n, such that if the absolute value of f sub n is less than 1, it's considered Gaussian, and if the absolute value of f sub n is greater than 1, it's considered non-Gaussian. So, is the distribution of fluctuations in our universe Gaussian? The answer is that we don't know yet, but we're trying really hard to measure it. One way to measure this would be to study the cosmic microwave background, since the perturbations evident in the CMB directly correspond to density fluctuations created during inflation. However, the CMB measurements contain many constraints that make it hard to get a very robust measurement. The best CMB measurement for Gaussianity today says that F sub L is probably less than or equal to about 14.3. CMB measurements are largely constrained due to cosmic variance and the fact that the CMB is a 2D surface, which limits the amount of Fourier modes we can measure. If we want a more robust measurement, we could try and measure these Fourier modes in 3D, which we can do by measuring the 3D distribution of matter in our universe, specifically galaxies and galaxy clusters. Specifically, how F sub L, this Gaussianity parameter, affects the distribution of matter is seen by this Doré et al. 2015 plot, which shows the power spectrum on the y-axis and K on the x-axis for different Gaussianity levels. So the white solid line shows a Gaussian distribution of matter, which has F sub L equal to 0. The yellow dashed line is right on the border between non-Gaussian and Gaussian with F sub L equals 1, and the blue dotted line is a non-Gaussian distribution of matter. This is F sub L equal 2. And here we can see that this Gaussianity parameter actually directly affects the distribution of matter in our universe, specifically at low values of K. So increasing the Gaussianity parameter increases the power spectrum at low values of K, meaning there are more density fluctuation Fourier modes at large scales. To help visualize this, here is a figure of some simulations done in Dalal et al. 2008. As we go down this figure, the value of F sub L increases, where this middle row shows F sub L equals 0, so this is for a Gaussian distribution of matter. For very low values of F sub L, we see that the dark voids are more evident than they should be, but for very high values of F sub L, the bright regions are more evident than they should be. Another way to visualize this, we could look specifically at individual galaxies. This is a plot from a SPHEREx paper, Doré et al. 2015. On the right-hand side, we have a Gaussian distribution of matter. On the left-hand side, we have a non-Gaussian distribution of matter. And if on this figure, we just focus on the blue dots, these are individual galaxies, we can see for a non-Gaussian distribution, the galaxies themselves are more clumped together. This tells us that there should be a way to directly study these galaxies to learn about the Gaussianity of the universe and hopefully tell us a lot about the physics that drove cosmic inflation. So, how can we measure this? Luckily, NASA has an upcoming mission called SPHEREx to try and constrain the physics of inflation by measuring the Gaussianity of large-scale structure. SPHEREx is an all-sky spectral survey that will launch in 2024 and last about 2 years. It will obtain near-infrared spectra from about 0.7 to 5 microns. Because it's an all-sky spectral survey, SPHEREx is going to gather tons and tons of really great data. For this topic in particular, what will be really helpful is it will gather over 1 billion galaxy spectra and over 100 million high-quality redshifts. With this information, SPHEREx will be able to create almost a 3D map of our universe, which we can use to measure the distribution of this matter. From there, we can constrain this non-Gaussianity parameter F sub L and learn a lot about inflation. Of course, SPHEREx has many science goals aside from just trying to constrain the physics of inflation. It will also study the origin and history of galaxies by measuring the extragalactic background light that makes up a lot of the light we see in our universe, and also study the origin of water in planetary systems by tracing the amount and evolution of some key biogenic molecules such as water, CO, and CO2. Aligning with CC ideals, SPHEREx is a very interdisciplinary mission, and Dr. Phil Moscow and Dr. Roger Windhorst here at the CC faculty are actually science members on this mission. But back to inflation. In order to build this 3D map of the universe, the SPHEREx team needs to be able to very accurately measure the redshifts of these galaxies. They will determine the redshifts for hundreds of millions of galaxies by fitting their measured spectra to a library of galaxy templates they have set up. This all-sky catalog they have is from the WISE, Pan-STARRS, and DES surveys. And this redshift fitting is going to be largely driven by the 1.6 micron bump that is nearly universal in galaxy spectra and a very powerful redshift indicator. In addition to getting actual redshift measurements, they're also going to get probabilities for all these redshifts. They hope to end up with 490 million galaxies at less than a 10% accuracy and 10 million galaxies at a 0.3% accuracy. These probabilities will allow the SPHEREx team to accurately determine F sub NL, the power spectrum, and the bispectrum for different accuracy bins. Here we have the observed galaxy density versus redshift for different accuracy bins, showing the range of redshifts SPHEREx intends to cover. For example, the orange line on the far left corresponds to a redshift sigma value of 0.003, meaning the redshifts in this bin will have a very high accuracy. The low accuracy bins, aka the dark and light blue curve, will constrain F sub NL in the power spectrum. The high accuracy bins will constrain the power spectrum itself and the bispectrum, which is a higher order moment of the density field. If we look just at the redshift range, we can see that SPHEREx will cover a range out to moderate redshifts, and therefore will rely on some other upcoming NASA missions such as Euclid and WFIRST to measure higher redshift objects and help us paint a complete cosmological picture of our universe. So, of course, one of the main goals of SPHEREx will be to constrain the physics of inflation very accurately by measuring some important cosmological parameters. Here on the y-axis, we have the running of the spectral index, alpha sub s. Alpha sub s pretty much just states how the spectral index, or tilt, of scalar perturbations in our universe changes with log k. On the x-axis, we have the non-gaussianity parameter f sub NL. And here we can see different constraints that different missions have provided. The big yellow oval is the constraints for which the Planck satellite allowed. The horizontal brown oval shows the constraints for which the Euclid power spectrum allowed. And the last three ovals show the constraints given by SPHEREx, which we can see is much better than the other two and will reduce the uncertainty by a factor of more than 10 times over the current values. The dark blue oval will constrain F sub NL from the SPHEREx power spectrum. The medium blue will constrain F sub NL from the bispectrum, and the tiny light blue circle in the center will be a combination of both of them. However, if you look carefully, you can see these constraints are kind of on the border between single field models and multi-field models. And SPHEREx really wants to try and determine whether inflation was driven by a single field model or a multi-field model. In order to try and accurately distinguish between these two classes of inflationary models, the SPHEREx team will also have to keep in mind that effects such as general relativity and some other nonlinear effects could produce signals that appear very similar to the non-gaussianity fluctuations produced during inflation. Detecting and trying to identify these signals will be crucial in ensuring SPHEREx accurately constrains the Gaussianity of matter in our universe. Overall, keeping in mind that the sensitivity of F sub NL measurements from the power spectrum and bispectrum will be extremely good, where the sigma value of F sub NL is about 0.87 for the power spectrum and 0.23 for the bispectrum, SPHEREx hopes to distinguish between single and multi-field models of inflation. Finally, there is about 1 million systematic effects that the SPHEREx team must accurately take into account to ensure their data is very reliable. For the sake of time, I'll just touch on a few of these. The diffuse light and extinction from within our own galaxy can contribute to systematic errors, as shown in this figure from Durrett et al. 2015, where it shows distributions of zodiacal light and diffuse galactic light and even cosmic rays. This includes light within our solar system, which is the zodiacal light, and interstellar gas. The SPHEREx team will use reliable and robust models to accurately account for all of these effects. There are also many systematic effects due to instruments that must be taken into account. This means having a very in-depth understanding of all the instruments on board SPHEREx, taking dark frames during the mission, and dithering during exposures to ensure these systematic effects are accurately modeled. To account for things such as source blending, they will identify redshift targets from prior catalogs and screen out blended galaxies using the higher resolution WISE and pan-star/DES images. Overall, SPHEREx is going to have a great legacy. To summarize, there are different models of inflation that predict various levels of Gaussianity in primordial density fluctuations. SPHEREx aims to calculate the Gaussianity of these density fluctuations by utilizing the power spectrum and the bispectrum. SPHEREx will also utilize the Fourier transforms of the 2- and 3-point correlation functions, which I didn't talk about in this talk. It will do this by classifying galaxies according to redshift accuracy after it measures the redshift of the millions of galaxies in its sample. They're hoping to get about 490 million galaxies at less than a 10% accuracy, which will drive the power spectrum F sub NL sensitivity. So again, this is this non-gaussianity parameter. The 16 million galaxies at a 0.3% accuracy will drive the bispectrum and some other inflationary parameters. SPHEREx will also complement Euclid and WFIR spectroscopic surveys, which focus on higher redshifts, and it will allow us to paint a complete cosmological picture of our universe. That's it, and I'll answer any questions in the discussion board. Thanks.